Welcome to Arise Online Chemistry class. Today we are going to discuss the second part of MCQs of Organic Chemistry, some basic principles and technique. Let us move on to the question. Arrange the following in correct order of acidic strength. So what do you mean by acidic strength? What is acidity? So if a compound can release H+, then we can call that compound as acids. So let us consider this compound CH3NO2. So I am expanding the CH3 as like this, NO2. NO2 is an example for an electron withdrawing group. NO2 is an example for an electron withdrawing group. So what happens is that this NO2 will pulls the electron of this carbon nitrogen bond towards itself. So what happens? This carbon will be electron deficient. So what this carbon do? Will pulls the electrons of CH bond towards it, which makes the CH bond polar and which makes the release of H+ easily. So presence of electron withdrawing groups in hydrocarbons will make the CH bond polarized and will make the release of H+. So presence of electron withdrawing group increases the acidic strength. So when you consider it, in all the compounds, 4 compounds, NO2s are given, and as the number of NO2 groups or as the number of electron withdrawing groups increases, what happens? The polarization increases and which makes the release of H+ easily. The one which is having greater number of NO2 will be the most acidic one. So which is having greater number of NO2? Fourth one is having greater number of NO2. So that is the most acidic one. Then you have second, then you have first one, then you have the third one. Why I choose between 1 and 2? Because in third you have only 2 hydrogens and 1 you have 3 hydrogens. Greater the number of H+ release, greater will be the acidic strength. Okay. So when you compare 1 and 2, I choose 1, then third. So which is the option? 4, 2, 1, 3. So which is option? It is option A. That is, presence of electron withdrawing group increases the acidic strength. Okay. Now moving on to the next question. Which is the most basic among the following? Okay. Basicity. What is a base which can donate a pair of electrons or which can donate a lone pair? Can be considered as what? Acid. There are other definitions also which can accept OH which can release OH minus can be called as a base, which can accept H+ can be considered as a base, or which can donate a pair of electrons can also be considered as a base. In all these ways we can define base. So let us consider which is the most basic among the following. Okay. So let us consider. So CH3NH2. So in nitrogen you have lone pairs. The one which have a greater tendency to donate that lone pair on nitrogen will be the strongest base. So when you consider CH3, CH3, CH2, then CH3 twice CHNH2 and NH3, so we can see that this CH3 groups and all the alkyl groups generally, alkyl groups are having plus-I effect or electron donating effect. So because of the plus-I effect of CH3, the CH3 will donate the electrons towards nitrogen, which increases the electron density on nitrogen, which makes the release of lone pair very easily. So the presence of alkyl groups on amines will increase the basic strength. So when you consider which is the most basic, A, B and D are amines and NH3 is ammonia. NH3 when compared with amines and ammonia, ammonia is least basic with ammonia because there is no any groups which can increases the electron density on nitrogen and which makes the availability of lone pair. Therefore, ammonia is least basic among this. Then you have to consider CH3NH2, CH3, CH2NH2 and CH3 twice CHNH2. Which of them is greater basic? So we know that the electron donating effect of primary group and secondary group and tertiary group. So, tertiary group is having greater electron donating effect, then comes secondary group, then have primary group. So, which is here in CH3 and CH3, CH2, NH2, primary group is attached to NH2, and in CH3 twice CH we have the secondary group is attached to it. So, when secondary group is attached to it, it is having a greater electron donating effect, so which increases the electron density of nitrogen at a greater extent. So, what happens, which makes the lone pair more available. So, therefore, option D is most basic. Okay. Now, moving on to the next question. Select the correct option for the stability of carbanions. What is carbanion? Carbon with a negative charge. Species are known as what? Carbanion. So, let us consider its stability order. We have already discussed the stability order of carbanions, that is primary greater than, secondary greater than, tertiary. This is the stability order. So, let us consider. So, we have first one is a primary one and the third one is a tertiary one. And what about the second one? It is benzyl carbanion, that is, this is the actual structure of benzyl carbanion, CH2 minus. This is the most stable one. Why? Because this carbanion, the negative charge on CH2 group, is involved in resonance with the pi electrons of the benzene ring, thereby it is stabilized. Therefore, benzyl carbanion is more stable. So, you have the second one, then you have the first one, then you have the third one. So, which is the option? It is option B. Okay. Now, moving on to the next question. Select the correct option for the stability of the following resonating structures. Again, a carbanion. Okay. So, let us consider. So, we have X, Y, Z. So, obviously, Y will be the stable one because it does not have any charge. Obviously, the presence of charge is an indication of destabilization. So, without charge will be more stable. So, obviously, Y is more stable. Then you have between X and Z. When you compare X and Z, in X the negative charge is on oxygen, more electronegative oxygen, and the positive charge is on electropositive carbon. So, and when you compare Z, the negative charge is on electropositive carbon. Carbon cannot hold negative charge for a longer time. Therefore, it is less stable. So, when you compare X and Y, which is less stable, Z is less stable. So, what is the order? Y is more stable, then X, then Z. So, which is, it is option C. Okay. Now, moving on to the next question. Again, which is something related to carbocation, carbanion, and which of the following is the least stable one? So, let us consider CH3, CH, CH3, CH3, CH2, CH2 plus, CH3C, CH3, CH3 plus, CH3 thrice C, CH plus C6H5. So, carbocation stability. There are two factors which decides the stabilization of carbocation. The first one is hyperconjugation and the second one is resonance. So, hyperconjugation, the number of hyperconjugated structures is equal to the number of alpha hydrogens. Okay, that you have to keep it in mind. Number of hyperconjugated structures is equal to number of alpha hydrogen. So, let us consider the first one. So, in this carbocation, hyperconjugation is only possible there. So, we can count the number of hyperconjugated structures. Greater the number of hyperconjugated structures, greater will be the stabilization. Okay. So, here you have two alpha carbons. What is alpha carbon? When in a carbocation, the positively charged carbon is the considering carbon. The neighboring carbon atoms are known as the alpha carbon. So, these are alpha carbons. So, how many hydrogens in alpha carbons? A total of 6. So, there are 6 hyperconjugated structures of option A. What about the second? Here there is only one alpha carbon and there is only 2 hydrogens. How many hyperconjugated structures? 2. What about the third one? You have 3 alpha carbons. So, the hyperconjugated structures is 9 because 9 hydrogens in total. So, what about this one? You have 9 alpha hydrogens. So, 9 hyperconjugative structures and in addition to it you have a benzene ring, right? Benzene ring constitute for a resonance. So in option D you have resonance as well as hyperconjugation. So which is the most stable one? D is the most stable one. Then you have C, then you have A, and which is the least one? It is option B is the least stable. Okay, so B is the least stable carbocation here. Now moving on to the next question. The correct order of stability of following carbon free radical. What is free radical? It is a species which containing an unpaired electron, and it is formed during the homolytic fission of carbon-carbon bonds or any bonds. Okay, it is due to the homolytic fission. Okay, and the order of stability of carbocation we have already discussed in the theory class, that is tertiary greater than secondary greater than primary. That is the correct order of what? Stability of free radicals. So let us consider these free radicals. Okay, so we have, this is the tertiary free radical, this is the benzyl free radical, this is primary and this is primary, and the free radical stability is also based on the hyperconjugative structures. Greater the number of hyperconjugation, greater will be the stabilization. So in CH3 thrice C, here you have CH3 C, CH3, CH3 dot. So you have 9 hyperconjugative structures. Then you consider this, here you have only 1 alpha carbon and 2 alpha hydrogen. So 2 hyperconjugative structures. Here hyperconjugation is not in the possible of CH3 free radical. What about the second one? It is benzyl free radical, which is have resonance. When you compare the stabilization with resonance and hyperconjugation, resonance stabilization is more prominent. So which is more stable one? Second one will be the more stable one. Then you have the first one, then you have the third one, then you have the fourth one. So 2, 1, 3, 4. So which is the option? It is option D. Okay. Now moving on to the next question. Which of the following is the most stable carbocation? So here all the carbocations are stabilized by resonance. Greater the stabilization, greater will be the resonance, greater will be the stabilization. So which is having greater number of resonance structures. Obviously option A is having greater number of resonance structures, so that will be having greater stabilization. So that is option A. Okay. Now moving on to the next question. Which one is the most stable free radical? Again a question related to the stabilization of free radical. That is the question what we are going to discuss next. So you have, let us consider this methyl Me is indicating the methyl group. Okay, it is indicating CH3. So this is a tertiary free radical. Okay, tertiary free radical. Here this is a allyl free radical. Allyl means C double bond C dot. These type free radicals are known as allyl. Okay. So the option C is also allyl, and option D is again tertiary. Here also an allyl group is there. Okay. Allyl and a tertiary free radical. Okay. So here the stabilization can be explained based on resonance as well as hyperconjugation. So let us consider, in option A you have resonance as well as hyperconjugation is possible. So based on the number of resonating structures and number of hyperconjugative structures, we have to assign the stabilization. So let us consider each of them in detail. Okay. So which is the first option? CH3. Okay. Here when you expand it, here you have a CH, here you have CH2, and this is the free radical. So how many? This is alpha, and this is alpha. 1, 4 and 6. So 6 hyperconjugative structures in total. In addition to it, there is resonance also. Resonance is also possible. Now consider the second one. CH2 dot. Okay. So this is the alpha carbon, it is H. Okay. So there is only one hyperconjugative structures, and also resonance is also there, but there is only one hyperconjugative structures. Now moving on to the next one. Here hyperconjugation is 1 because there is only one alpha hydrogen, so there is only one hyperconjugative structures, but in addition to it you have resonance. Here in the third one you have only hyperconjugation, 9 alpha hydrogen, so 9 hyperconjugative structures. So if there is hyperconjugation plus resonance, that will leads to more stabilization, so which is having greater stabilization. Option A will be having greater stabilization due to greater number of hyperconjugative structures and greater resonance stabilization. So which is the option? Option A is the correct one. Okay, so it is option A. Now moving on to the next question. Which of the following is the most stable alkene? Alkene can also be, alkene stabilization can also be considered by hyperconjugation, because hyperconjugation is also possible in alkenes. Greater the number of hyperconjugative structures, greater will be the stabilization. That is also based on the number of alpha hydrogens. Alpha hydrogen means the double bonded carbons are the considering carbons, the neighboring carbon atoms will be considered as the alpha carbon, and the hydrogen present in is known as what? Alpha hydrogen. So here this is the double bonded carbons, there is no alpha carbon at all, so there is no alpha hydrogen. Now here in this is the double bonded carbon, this is the alpha carbon, you have 3 alpha hydrogens, so 3 hyperconjugative structures. Then here CH2 CH3, so we have 1 alpha carbon and 2 alpha hydrogen, so 2 hyperconjugative structures. Here there is only 1 alpha carbon and 1 alpha hydrogen, so 1 hyperconjugative structures. So which is having greater hyperconjugation, that is option B. You have 3 hyperconjugative structures. So which is the option? It is option B. Now moving on to the next question. Which of the following is an aromatic compound? That is the next question that we have to discuss. How we can predict an aromatic compound? Aromatic compound is predicted by Huckel's rule. What is Huckel's rule? For a compound to be aromatic, it must be planar and it must possess 4n plus 2 pi electrons. Okay. Based on that, 2. This is what? Naphthalene. In theory class, I have already discussed naphthalene is aromatic, right? Because I will check the 4n plus 2 pi electrons for this compound. That is 4n plus 2 is equal to how many pi bonds? 1, 2, 3, 4, 5. 5 pi bonds is equal to 10 pi electrons. Okay, 10 pi electrons. So 4n is equal to 8, where n is equal to 2. So what is Huckel's rule? For a compound to be aromatic, it must be planar and it must possess 4n plus 2 pi electrons, where n is an integer. Here in option B, n is equal to 2, so it is an integer, so it is aromatic. Now similarly, you can also calculate the aromaticity of this compound. In this compound, when you consider, you have to consider the lone pair on nitrogen also. Okay, then only you will be able to calculate the total number of pi electron, because that is also involved in resonance. So when you calculate the aromaticity, you will be able to find out that B and C both are aromatic. So which is the correct option? It is option D. So you can check the aromaticity by Huckel's rule. Now moving on to the next question. Which is aromatic compound among the following? When you consider all the compounds are aromatic. Okay, the option C is pyridine. Okay, so here when you consider it, pyridine is actually, it is like this when you consider the pi electrons. Okay, here also we can assign what? Aromaticity by Huckel's rule, then it follows Huckel's rule. So all the compounds are aromatic. So it is all the above. So it is option D. Now moving on to the next question. The strongest deactivating effect on aromatic ring. So what are deactivating group and what are activating groups? Deactivating groups means which pulls the electron from the benzene ring when it is attached to the benzene ring. I already said that all the meta-directing groups are deactivating groups in theory class. So which are the meta-directing groups? Cn minus, CHO, COH, C double bond O, NO2, all these groups are meta-directing groups, and when these groups are attached to the benzene ring, it pulls the electrons of the benzene ring. Such compounds are known as deactivating groups. So what are activating groups? When a group is attached to the benzene ring, it gives the electrons to the benzene ring. They are known as activating groups. Out of this, CH2Cl, OCH3, CH3 all are orthoparadirecting. All orthoparadirecting are activating groups except halogens. So out of this, which is the deactivating group? CCl3 is the deactivating group. So it is option D. Okay. Now we can move on to the next question. Identify the correct order of reactivity of electrophilic substitution of the following compounds. So, orthoparadirecting group or activating group will increases the tendency for electrophilic substitution reaction. What is an electrophilic substitution reaction in benzene compounds? What is happening? The hydrogen atom in the benzene ring will be replaced as H plus by the incoming electrophile. That is known as electrophilic substitution reaction. So, for an electrophile to attack, electrophile is preferred to attack where there is electron density is higher. And we know that activating groups, mainly orthoparadirecting group except halogens, what happens is they are giving the electrons to the benzene ring, which increases the density of benzene ring. Thereby electrophilic attack will be very easily. So, orthoparadirecting group and or we can say activating groups will increases the tendency for electrophilic substitution reaction, and meta-directing groups, that is deactivating groups, which pulls the electrons of the benzene ring, which decreases the electron density, thereby decreases the tendency for electrophilic substitution reaction. Based on that concept, you are able to answer this question. So, here which are the groups given? So, here CHO, CH3, NO2, Cl. CHO is a deactivating group, but CH3 is an activating group. So, that is should have the greatest electrophilic substitution tendency. So, obviously, this is a wrong option. Then you have NO2, CH3, Cl, NHCH3. NHCH3 is also an activating group. Cl is a deactivating group. CH3 is a activating group. So, here this should be in this order. The first electrophilic substitution is for NHCH3 groups, then it is for CH3, because in NHCH3 group it increases the tendency for electrophilic substitution by resonance effect, and CH3 increases the tendency for electrophilic substitution by hyperconjugation. So, resonance is more dominant, so which is having greater order of reactivity for electrophilic substitution. NHCH3, then you should have a toluene, that is benzene with CH3 group. So, this option is also wrong. Then coming to next, CH3, NO2, CHO, Cl. So, when you consider these things, CH3 should have the greater tendency for electrophilic substitution, then it is not NO2, it should be chlorobenzene. Why chlorobenzene? Chlorobenzene have two types of effect. It has plus R effect. Plus R effect means it gives the electron to the benzene ring through resonance, and it pulls the electrons from the benzene ring through minus I, that is negative inductive effect. So, both effects are there, but resonance effect is dominating. So, the next should be what? Chlorine, chlorobenzene. So, this is also the wrong order. So, obviously, which will be the correct one? Option D will be the correct one. You have NHCH3, then you have CH3, then you have Cl, then you have NO2. NO2 decreases the electron tendency by resonance. So, it is least reactive for electrophilic substitution reaction. Okay. So, which is the option? It is option D. Now, moving on to the next question. Most stable carbocation. Okay. So, carbocation stabilization. So, let us consider, if there is an electron withdrawing groups, it will decreases the electron density of benzene ring, thereby increases the positive charge. Similarly, electron releasing group will increases the electron density and thereby decreases the positive charge. So here we can see that in the first one all the carbocations are similar, only difference in the group. One you have chlorine, another you have NO2, the other you have OCH3. Chlorine or NO2 are deactivating group, where OCH3 is the activating group, which gives the electron to the benzene ring, which in turn gives the electron to the CH2 group, right. So the charge dispersal is dominant in the case of option C. Thereby, it is the more stable carbocation, that is option C. Okay. Now, moving on to the next question. The most stable carbocation, actually it is not carbanion, it is carbocation, because the option given are carbocation among the following. Okay. So, here also it is based on hyperconjugation and resonance. So, here in the first carbocation, resonance is not possible for the carbocation, but in benzene ring it is resonance possible. So here the stabilization is based on hyperconjugation. This is the alpha carbon, 2 alpha hydrogens, so 2 hyperconjugative structures. Here you have resonance. Here you have an activating group in addition to resonance, you have a deactivating group in addition to resonance. So which is the most stable one? Option C will be the most stable one. Why does option C? It has resonance stabilization. In addition to it, there is an electron donating group which increases the electron density, thereby reducing the magnitude of positive charge. So which is the most stable? Option C is the most stable. Then you have to find out which is the most acidic compound. Acidic compound means which has the tendency to release H plus, or which compound will makes the OH bond more polar, can be considered as the most acidic. The first one is phenol, second one is benzoic acid, and you have C and D are benzoic acid. Okay. So when you consider phenol and benzoic acid, obviously benzoic acid are more acidic than phenols, because of their stabilization of carboxylate ion by resonance. And when you consider COA, benzoic acid and the substituted benzoic acid, so presence of electron withdrawing groups increases the acidic strength and presence of electron releasing group decreases the acidic strength. So when you consider CH3 and NO2, NO2 is the electron withdrawing group, so it decreases the it increases the acidic strength, where CH3 group decreases the acidic strength. So which is most acidic? D, that is nitrobenzoic acid is the most acidic compound, that is option D. Now moving on to the next question. Among the following, which is the strongest base? So we have aniline, that is C6H5NH2. Then you have para-nitroaniline, then you have meta-nitroaniline, then you have C6H5CH2NH2. This is an amine. It is not an aniline derivative, it is an amine. So when you consider amines, ammonia and aniline, amines are more basic because of their electron donating effect, and anilines are less basic because of their resonance, because the lone pair on the NH2 group is involved in resonance, thereby the lone pair on NH2 group is not available, therefore it cannot donate lone pair, therefore it is less basic. But amines are more basic because the plus I effect, or the electron donating effect of the alkyl groups, which increases the electron donating electron density on nitrogen and which makes lone pair more available. So option D, because it is an amine, it is not an aniline derivative. Now arrange in the decreasing order of their basic strength. Okay, you have aniline, then you have NO2 group, then you have cyanide, then you have CH6. So in basic strength, presence of electron releasing group increases the basic strength and presence of electron withdrawing group decreases the basic strength. That you have to keep it in mind. Presence of electron releasing group like CH3 increases basic strength and electron withdrawing group decreases the basic strength. Okay. So let us consider, here you have aniline, then you have derivatives of aniline. In NO2, CN, both are electron withdrawing. Then you have CH3, which is electron releasing. So presence of electron releasing group increases the basic strength. So which is more basic? Obviously the fourth one. So you have two options, which is in which the fourth is having greater basic strength. So you can cut off two options, that is option B and option A. Okay. Now out of option C and D, which is the correct one, so obviously when you are comparing with aniline, the one which is having electron releasing group will be more basic than aniline, and the one which is having electron withdrawing group will be less basic than aniline. So after this one which is having CH3 group, after that aniline should be there. So which is 4, 1, then out of 3 and 2, which is, so when you compare the electron withdrawing effect of NO2 and cyanide, cyanide is more electron withdrawing, so that will be least basic. So it is option, sorry, NO2 and cyanide, NO2 is the more electron withdrawing effect, so therefore NO2 containing aniline will be the least basic one. So it is option C. Okay. So you have to go for the electron withdrawing effect of group. So NO2 is having the greatest electron withdrawing effect. The one which is having NO2 will be having the greatest electron withdrawing effect, thereby withdraws the electrons of the benzene ring, which in turn withdraws the electrons of the NH2 group. Thereby it cannot donate lone pairs, thereby it is least basic. Okay. So it is option C. That is first which contains CH3, then you have aniline, then containing CN, then you have NO2. Okay. Now moving on to the next question, which of the following is the strongest base? Obviously it is again something related to the basicity of base. You have aniline, aniline derivatives, and you have, this is primary amine, this is secondary amine. Okay. Okay, here you can see that which is more basic. So D will be more basic. Why it is so? I will explain. Aniline, why it is not basic? Why? Because in aniline, the nitrogen lone pair is involved in resonance with the benzene ring, thereby it cannot donate the lone pair, therefore it is less basic. Then you have similar, option C is also like that. Then you have option B, it is a secondary amine. You have an alkyl group as well as what? A benzene ring, because in the presence of the benzene ring again decreases the electron density of nitrogen, thereby it cannot donate the lone pair. But in option D, it is a primary amine, it is not an aniline derivative. Here it is NH2 group is directly attached to the CH2 group, which is having an electron donating effect, thereby increases the electron density on nitrogen, therefore the nitrogen can donate the lone pair, therefore it is the strongest base. So the option D is an amine, it is not an aniline derivative. So it is option D. Okay. Now we have the next question, which of the following compound shows dipole moment? Okay. So here 1,4-dichlorobenzene. So this is 1,4-dichlorobenzene. Here carbon chlorine bond is polar, therefore carbon chlorine bond will have a dipole moment, and the dipole moment direction will be towards chlorine. So both the carbon chlorine bond will have a dipole moment, that will be to in the opposite direction. Because of that, both the dipole moment are in opposite direction, they will be cancelled out. So therefore dipole moment is 0. Okay, that is for 1,4-dichlorobenzene. Then trans-2-butene. We already discussed when we discussed geometrical isomers, that is cis and trans isomers. Trans isomers does not have a dipole moment because the dipole moments are cancelled out. Here let us consider trans-2-butene. C double bond C, CH3, H, CH3, CH3. So since not CH3, H. So here the dipole moment gets cancelled out because they are diagonal to each other. Then trans 1-chloropropene. So let us consider this one, whether this trans has a dipole moment or not. Trans 1-chloropropene, C double bond C, Cl, H, CH, CH3. Here you can see that. Let us consider the trans form. I have written the cis form, CH3H. What is 1-chloropropene? It is CH3, C, double bond C, Cl. So now I have to substitute for the valency, CH, okay. This CH3, CH, double bond CH, Cl. This is 1-chloropropene. It is in trans form with respect to hydrogen. If hydrogen is on the opposite side, it is trans. If it is on the same side, it is cis. Because you have two different groups, that is one is CCl group, one is CCH3 group, their dipole moment are entirely different. Even though they are trans to each other, but they are having the magnitude of, they are having a different magnitude for dipole moment. Even though they cancelled out, it is not completely cancelled out because the groups are not the same. In the case of 1,4-dichlorobenzene, both are having dipole moment and both are same group, so their magnitude is also same. That is why, since they are opposite to each other, they cancelled out. But here in 1-chloropropene, carbon-chlorine bond is having a dipole moment, CCH3 bond is also having a dipole moment. They cancelled out, but it will not completely cancelled. Why? Because both are having a different magnitude of dipole moment, both are different groups. So, which is having a dipole moment? Trans 1-chloropropene. Then what about trans 1,2-dichloroethene? So, it is C double bond C, Cl, Cl, H, H. What about this? Here the groups are same, so the dipole moments get cancelled out. So, this is having a dipole moment 0. Why this trans is having a dipole moment? Because it is not trans. Why? Because they are having different groups attached to it. Okay. So, it is option C. Okay. So, this is about the MCQs of organic chemistry, some basic principles and technique. I hope all you understand. Thank you.